x1 square plus 3x1 x2 minus 2x2. Okay, so this polynomial has degree 2 and it has three monomials, right? One is x1 square, the other is 3x1 x2, the second one is minus 2x2. So now we want to understand how to compute this polynomial. So what does it mean to compute a polynomial? So I want to understand how many additions and multiplications are required to compute this polynomial. In some sense, if you give me a1 and a2, which are substitutions to x1 and x2, how many additions and multiplications are required to find the value of f at these points, at the given point. So if you were a programmer or a computer scientist and you were asked to write a program to do this, you will probably write a sequence of instructions like this, right? So that is a straight line program. So it has a sequence of instructions. So the first instruction squares x1, the second instruction does x1, x2, the third instruction does 3 times the second instruction and so on. And the last instruction actually computes this polynomial. Okay. So one way to actually view this polynomial graphically is the graph on the right hand side, right, where you have a set of gates or nodes. So this is a directed acyclic graph. So the graph has some directions, it has no cycles. The leaves in this graph are labeled by variables, x1, x2 and so on, right? Or they may be labeled by constants, right, depending on your usage. And internal gates or nodes, internal vertices in this graph are labeled by either addition or multiplication. So bottom up, if you look at it, this gate computes x1, x2, this gate computes the sum of its children and so on. So a gate labeled by plus computes the sum of its children, a gate labeled by product computes the product of its children. And one of these gates, so we'll call them gates, one of these internal vertices is actually labeled as the output. Right? And that is the one that actually computes this polynomial, x1 square plus 3x1 x2 minus 2x2. Okay. So is this model clear? So the constants here come from some field depending on your polynomial. Is that okay? So what are we interested in? We want to understand the number of additions and multiplications that are needed to compute, let's say, this polynomial. So what is the number of additions and multiplications correspond to in this graph? The number of internal vertices. Right? So we'll call that the size of the circuit, which is the number of gates in the circuit or the number of arithmetic operations. We'll also be interested in the depth of the circuit, which is the length of the longest path from input to output. For example, this circuit has depth 4 and it has size 6. So is it okay, like what is size and what is depth? So there may be several ways to compute a given polynomial. So let's take an example. For example, this one. You have 1 plus x1 plus x2 plus so on plus xn, and then all degree 2 terms, x1, x2, x2, x3, x3, x4 and so on. There are n, choose 2 of them. And then all degree 3 terms, degree 4 terms, and one monomial that does x1, x2 to xn. So could you, one math way of writing this is you're going to sum over all subsets from 1 to n except the empty set. Look at those variables that are indexed by this set, xi. So can you describe a circuit or what is the size of a circuit computing this polynomial? 2 power n, right? So you have one sum gate followed by 2 power n children, product gates, and each of the product gate computes the corresponding monomial, right? So that is one way of computing this polynomial. So now can you ask, is there a cleverer way? So that roughly requires like 2 to the n many multiplications, product gates, right? So the question is, can you do this better, in a better way? So here is a better way to do this. 1 plus x1 times 1 plus x2 times 1 plus 1 plus xn times minus 1, right? So this, by investing just n minus 1 multiplications, you can compute all the 2 to the n possible multilinear monomials. This is like picking subsets from 1 to 2n. So this requires 2 to, this circuit, if you drew out a circuit for this, this would have like 2 to the n many multiplications. Here this has n minus 1 multiplications, right? So now there are different ways to compute the same polynomial, meaning there are different circuits you can draw, and circuits can have drastically different size, right? Despite the polynomial having this representation. So now you can ask, what is the best way to compute a given polynomial? So if I give you a polynomial, what is the smallest circuit for it? Maybe even this is not clear, right? How do you show that this is not? So let's see some basic observations about circuits. So the first thing is a circuit of size S can actually compute polynomials of degree like 2 to the s by repeated squaring. So this is x1 square, x1 power 4, so on up to x1 to the 2 to the s. right? So here. So by investing log n gates, you can actually compute polynomials of degree n, right? Because of this repeated squaring, right? And this is still directed acyclic. So it fits in the definition. Now, what can you say about general polynomials on n variables, degree d? So there it was a specific example. So here, if you are given an n varied polynomial of degree d, what is the first circuit you will probably draw? Correct. So you'll write down the sum of monomials representation, so many multiplication gates you need. So how many monomials can an n varied degree d polynomial have? Can you count? And the degree also, right? Degree also. So you have to choose d things from n things with repetition, right? That's how you form a monomial. Right? So you can always compute it by a circuit of this size where the depth is 2. You have one addition gate followed by multiplication gates. Each multiplication gate is computing a monomial. Is that okay? So now this is one way to compute an invariant degree polynomial. Is this the best way? Right? That depends on the polynomial. So let's try to see some other observation. So think of this rectangle as all those polynomials on n variables with the degree d. For convenience, let's say that the coefficients are all 0, 1. So in principle, coefficients can be anything from the field. And when the field is not finite, I mean, you cannot really draw this as a box, right? It's an infinite. There are infinitely many polynomials and n variables with degree d depending on the field. But let's say they have only 0, 1 coefficients. So then how large is this box? You have n plus d choose d many monomials, and for each monomial, the coefficient can be 0 or 1. Right? So this box has like dimension 2 to the n plus d choose d at most. Now inside this, you have polynomials whose coefficients are 0, 1 and are computable by circuits of size at most s. So this independently I can count. I'm going to assume that the field is finite, otherwise counting does not make sense. So how large is this? You can bound this to be at most 2 to the order s square. This is because every circuit is actually a graph, a directed acyclic graph. So you can count the number of directed acyclic graphs. So I'm also assuming a bit that the fan in and all is 2, right? Every vertex has 2 children and so on. And I can count this. Now this has a count, this has a count, right? I know that every polynomial can be computed by a circuit and maybe one polynomial is computed by many circuits. Right? So the number of circuits is at least the number of polynomials. So this means that there exist things in this outside set, right? In the rectangle minus the circle, such that the size is at least square root of n plus d choose d. Because 2 to the order s square is this, which means that s is at least square root of n plus d choose d. So what does this tell us? This means that every polynomial can be computed in this size, and there are polynomials that require so much size. There exist polynomials with 0, 1 coefficients on n variables degree d that require size square root of n plus d choose d. At least this much, right? So at most is this, at least is this. So the only difference is a square root. So this is actually open. So it's not clear if we can make this statement that any n varied degree d polynomial can be computed in size root of n plus d choose d. So is this tight? That's open. So there are polynomials here which require large size circuits. So n plus d choose d is quite large, right? It's exponential. Now the question is, can you tell me what it is? Can you describe a polynomial that requires large size circuit? So what is the meaning of that? No matter how I draw it as a graph, the number of operations needed is at least this much. So if you ask me, is there one? And the answer is yes, because we did just a counting argument and said that there exists one. But if you ask me what this polynomial is, then I have no idea. So I don't know how to describe this polynomial. So that's what we want to understand. Okay. So there exists n varied degree d polynomials, in fact, with 0, 1 coefficients that require this much size. That's what we proved using a counting argument. This also holds over infinite fields, but over infinite fields, you have to do a dimension counting. You can't count like this with hands. Okay. So let's see some examples of polynomials and then try to understand what is going on. So here is a matrix. It's a 3 cross 3 matrix. The entries are symbols instead of numbers. Okay. So x1, 1, x1, 2, so on up to x3, 3. The determinant of this matrix can be described like this. So I've just written out the determinant. So the determinant is actually now a polynomial in n square variables because it's an n cross n matrix. This polynomial has degree n, right? Because from every row you are picking one element and from every column you are picking an element, exactly one element in the determinant. And it has a lot of monomials, and this polynomial is homogeneous, meaning that every monomial has degree exactly n because every monomial is found by picking exactly one element from each row and each column, right? So it's a homogeneous polynomial. So how many monomials does the determinant have? Sorry? N factorial, right? N into n minus 1 into, that's how you would expand the determinant. So there is a circuit for the determinant that has size n factorial, a depth 2 circuit, right? Compute the determinant monomial by monomial. But do we know of better ways to compute the determinant? Like, or Gaussian elimination, right? So these are some algorithms in high school or procedures we have seen to compute the determinant. So if you look at Gaussian elimination, the thing is we have to pick a non-zero pivot, then you have to divide by the pivot. Right? These are operations that you do in the determinant, but it's not clear a priori how to draw a circuit from it because we only used addition and multiplication. We didn't use division, and Gaussian elimination uses division. Right? In fact, it also asks you to check whether the chosen pivot is non-zero. So it's not clear how to draw that using a circuit, but there are ways to do it. So given a circuit with divisions, you can completely eliminate divisions. But at least at the moment, we have not described it. Right? So is there a way to do it just with addition and multiplication? So this is a circuit for determinant, but this is a bad circuit. It has like n to the n size roughly. So can you, so there is a there's an easy algorithm for determinant. So is there a better way to draw this circuit? So how do you compute the determinant usually, like in high school? Expand along the first row. That's your sigma, right? And then for each thing, you look at the corresponding minor and then multiply. This is sort of an expansion. So for determinant of a 1 cross n matrix, there is a small circuit, just that variable. For an n cross n matrix, you have one sum gate with n children, and you'll have to compute these determinants. So inductively, you can assume that they all have small circuits. So the overall, by induction, you can prove that there is a circuit for determinant of size polynomial in n. It's not a hard thing to prove. Your Gaussian elimination also actually does that. It's just that Gaussian elimination uses some division, which at the moment it's not clear how to eliminate. So determinant, now when viewed as a polynomial, where the entries of the matrix are not numbers but symbols or variables, has a small circuit. So small here is polynomial in n, right? Maybe n cubed, n power 4 and so on. Is that okay? So let's describe another polynomial, which is the permanent of a matrix. So here is a matrix, the same matrix that we used last time. I'm going to describe what is called the permanent. So the permanent is the same set of monomials as the determinant, but there is no sign. Okay, everything is sum. So I just put plus, plus, plus. So it's the usual determinant and permanent are actually twins. Right? It's just that the sign is not there in the permanent, but there is a sign in the determinant. So how many monomials does the permanent have? N factorial. So there is another circuit of size n factorial for permanent that is also homogeneous polynomial degree n square variables. Right? Everything is the same. So now the question is, can we do something like what we did last time to compute the permanent? Right? Some sort of an inductive argument. So how do we compute the permanent? So what we know currently is there is a circuit for permanent of size n factorial. I want to ask, is there a better circuit? So how do you compute the permanent of this matrix? I've just filled in A, B, C because it's difficult to write x1, 1, 2, x. So this is one way to compute the permanent. 3 factorial is 6, so there are 6 monomials. But are there other ways to compute the permanent by looking at this matrix? Can you say something? For example, what if I sum the rows and take the product? I mean, sum the columns and take the product. So it's A plus B plus C times D plus E plus F times G plus H plus I. So this contains the permanent. Right? All the terms in the permanent are actually in this product. But the problem is, so what is the problem? Sorry? Correct. So it contains permanent and many more terms that are not in the permanent. Right? So it has included the permanent, but there are many other terms which you have to exclude. So one way to exclude them is to choose these two rows and take the sums and subtract. So anything that has two things from the same row will now go away. Right? So for example, AEH is not a valid monomial in the permanent, that is flushed. Okay. So similarly, I can subtract terms. Now in the process, if you look at it, some of the terms which were actually in the permanent may have been excluded. Right? So you have to include them. Right? So you start with a product of sums, which includes the permanent and some more terms, so you have to exclude them. And in the process of excluding, you may have excluded some other terms actually in the permanent, you have to include them. So what principle is this? Inclusion exclusion, right? So you can write down a expression for permanent using inclusion exclusion principle. So this is a classic example of applying inclusion exclusion. So how large is this circuit? How many gates does it have? Addition, multiplication. Roughly like 2 to the n times n square. Right? Yeah, and then some more gates you will need to do this, right? So 2 to the n many, so there's a sum gate on top with 2 to the n children, and then for each of those children, you will have to do some sums. This sum, where the size of the set S could be at most n. So roughly like n times 2 to the n, which is better than n factorial. So we started with a circuit for n factorial, you have reduced the size down to n square times 2 to the n. Now the question is, can you do something better than this, like Gaussian elimination that you did for the determinant? Right? So we don't know any circuit for the permanent that has size polynomial in n, and we believe that any circuit for permanent requires size 2 to the n, 2 to the omega n. So determinant had a small circuit. Permanent is not known to have a small circuit. Determinant had the sign, but the permanent does not have the sign. But it is this sign that actually helps you compute the determinant, because there is a minus sign, things can get cancelled. But the power of cancellation is not there here, so we don't know how to use Gaussian elimination. So these are like non-identical twins. Okay. And the set of monomials is the same, but once the moment the sign is flashed, right, things become easier to handle. So this slightly better circuit for permanent is known, I think n times 2 to the n due to Glynn, but we do not know of any circuit that's better than this. So this is a well-known open problem. It's called the determinant versus permanent problem. Okay, so now we know how to compute the determinant. We don't know how to compute the permanent. Okay? So one way to prove this is to say that look at this permanent, no matter how you draw this as a graph, that graph will have so many gates. And that's how you try and prove this argument. Okay? So this was conjectured in 1979. Still, even now we don't know how to prove this. So what is the best we know? We know that given this polynomial, which is not the permanent, it's a different polynomial. It's a polynomial of degree d in n variables. It's just x1 to the d plus x2 to the d plus xn to the d. If you draw this as a circuit where every gate has spanning 2, right, then the size will be omega n log d. So that's an argument we know from 1983, and that's the best we know. So these are called proving lower bounds for polynomials computed by arithmetic circuits. This is saying that any circuit must have size at least this much. So it's a lower bound argument. So one nice thing to note here is there is also a circuit of size n log d for this polynomial. So you repeatedly square x1 log d times, like what we saw, and then repeatedly square x2 log d times, xn log d times. So there is a circuit of size order n log d that computes this polynomial. So it's a matching upper bound and a lower bound. You know nothing better than this. For some special cases, we are working on better lower bound. So special cases where the graph is not allowed to be, there are no crossings, it's planar, the graph has to be a tree and so on. But in the general case, it remains open. Okay, so we know how to compute the determinant, we don't know how to compute the permanent. So what not only a scientist but a layman would do is write the permanent as the determinant. Right? You know how to compute one, you don't know how to compute the other. So you're given one matrix, right, whose permanent you want to compute. Come up with another matrix whose determinant is the permanent of this matrix. So if it's a 2 cross 2 matrix whose permanent I want to compute, I'll take that 2 cross 2 matrix and negate this entry. Right? So now the permanent of this is actually the determinant of this. And I know how to compute determinant. Right? So I can use it to compute the permanent. So this is what Polya observed in 1913, even before we actually studied determinants from a computational perspective. So now the question is, can you do this for 3 cross 3? So can you express the permanent as the determinant of a different matrix? So for every n cross n matrix, whose entries are xij's, is there another n cross n matrix n, right? Such that the permanent of M is the determinant of n. But now the entries have some sign change, plus minus xij's. So this was answered no immediately. It is not possible. If you look at the same matrix and do this surgery, like just flipping the sign, then it won't work. Okay? So what does this mean? You cannot just flip the sign and keep the dimension the same. Right? So in this question, what was answered was that you can't just flip the sign from plus minus, or maybe do some small enough substitution like setting things to 0, 1, minus 1 and get the permanent to be the determinant. So either the entries need to be more than variables or sign changes, or the dimension of the matrix has to grow. Is it okay? So now the question is, given a matrix M, right, whose entries are xij, okay, this has to be M cross M, right? Is there another M cross M matrix? So the original matrix is N cross N. Now I'm going to construct a slightly larger matrix, possibly M cross M. Right? The entries there were xij. Now these are fij's, some other polynomials, such that the permanent of M is the determinant of N. Right? And these fij's are not too complicated polynomials in xij's. So they're linear. I mean, otherwise, if you run the determinant algorithm, you are feeding in polynomials that are already very hard. So it doesn't make sense, right? And the matrix dimension should not blow up by much. From n cross n, you only go to poly in n cross poly in n. Right? So in principle, then this means that if you've seen a bit of computer algorithms, if you have an efficient algorithm for the determinant, you will also have an efficient algorithm for the permanent. You can use the same algorithm. Right? You don't have to do much. Whenever I'm given this matrix M, I'll have to produce this matrix N, right, which does not have too complicated entries. These are all degree 1 polynomials, and then I'll use the algorithm for the data. Okay. So this question is largely open. So what is this called? This question is called the determinantal complexity of permanent. So it's a complexity of expressing the permanent of a matrix as the determinant of another matrix. It's called determinantal complexity. So what Grenett showed in 2012 is that if you give me an n cross n matrix M, right, I'll produce another matrix capital N, right, with just 0, 1, minus 1 or xij's as entries, right, and the determinant of N is the permanent of M. But the problem is this matrix N has really large dimension. Like from N, you are growing to 2 to the N minus 1 to cross 2 to the N minus 1. So there is a large matrix whose determinant is the input matrix permanent, but this is relatively large, but the entries are quite simple. It's just the same entry or maybe some substitutions. So he gave an explicit construction. He drew a big matrix that used this small matrix. So the M in the previous question is at most 2 to the N minus 1. And Minion and Rezer in 2004, they used a bit of algebra to show that you will have to grow the dimension by at least n square by 2. Okay, so this is an upper bound, this is a lower bound, there's a lot of gap. So we don't know how to improve this. Right? So the determinantal complexity of permanent is open. The determinantal complexity of some other polynomials have also been studied. Like you look at some other polynomial. Can you write it as the determinant of some matrix with some entry substituted? Okay, so that's the determinant versus permanent question. I want to talk about another question which also has some connection to determinants. Okay, so I don't know if you've seen, but a polynomial is identically 0 if all its coefficients are identically 0. So for example, this is an identically 0 polynomial, this is not. Right? Because I've changed the sign. Now there is this computational question of asking, given a polynomial which is n variate degree d, right, can you test whether it is identically 0? In some sense, if I give you this polynomial, you should say yes. In this polynomial, you should say no. Right? You should design an algorithm to do this. One way to think about it is to try and automate proving mathematical identities. Right? So these kinds of identities can be tested using an algorithm. So there is something written here that given f. So it's not clear how you give f to an algorithm. Right? If you have to design an algorithm. So one way to give f is actually describe f. Right? Write down all the coefficients. Monomial by monomial. Then it's not very hard. You can just run over the monomials and coefficients and check if all of them are 0. So it's not meaningful. And that algorithm will require large time because the input itself is described using a vector of length n plus d choose d. At all the monomials coefficients you have to explain. So there are two other ways to, more sensible ways to give the input. Right? So one is the black box model where you are allowed to query the polynomial at certain points. Right? So you can assume that there is a box. If you feed in a, this box will output f of a. From these evaluations, you have to learn whether the polynomial is identically zero or not. Another model is the white box model. So we know how to describe a polynomial as a circuit. Right? So you give the graph representing the polynomial as an input to the algorithm, and the algorithm should use this graph to decide whether f is identically zero or not. So let's do some toy examples and then maybe I'll stop. So consider this univariate case. Okay? So you are given a univariate polynomial of degree d, and we want to come up with a procedure to decide if f is identically zero or not. And let's assume we are in the black box model. So you can ask me what the value of f is at a certain point, and I will tell you. So can you try to design a procedure? Sorry, just one variable. Something like x1 square plus x1 plus 2. So univariate polynomial of degree d has d plus 1 monomials. One constant term and then. So is there a way to describe? You ask f of 0, you get the constant term. If it's non-zero, then the polynomial is not identically zero. If it's 0, so what values do you ask? That's the question, right? So you may ask the box some value. That's right. So you ask the box a value and the box will return 0 or non-zero, something, right? So you don't know what to ask the box currently. You see a polynomial, that's all, right? So you may ask the box the value at a point. If it returns something non-zero, then you know that the polynomial is not identically zero. It evaluated to a non-zero point, right? But you may ask some point and it may say 0. So it may be that the original polynomial was identically 0, or you incorrectly queried at a root of the polynomial. Right? That's the only possibility. Like for example, the polynomial would have been x1 minus 2, and you just ask the box for the value of f at 2. It would say 0. So you have to keep asking the box. So how many times will you have to ask the box until you can be sure? D plus 1, right? So you know that it has at most d roots. So if I ask the box d plus 1 times and all the d plus 1 were actually 0, then the polynomial is identically 0. But if in this run, if the polynomial is not identically 0, it would have had at most d roots. So in at most d of the values, you would have gotten unlucky. One of the points will tell you it's not identically 0. So if it has at most d roots, so with the d plus 1 queries to the black box, you can actually answer this. So what about multivariate? How many roots can a multivariate polynomial have? So for example, x square plus y square minus 1 can have infinitely many roots, right? All points in the unit circle are roots. So you cannot do this. You cannot count the number of roots, so you'll have to do something better. Right? So like few minutes. Yeah, so it's the last slide. So maybe I'll do it. Okay. So let's say that now you are given. So what did we learn from the univariate setting? If you are given a polynomial, this is a univariate polynomial with coefficients from a field and degree is d. And let's say I pick, so I don't know what point to query on. So I'm going to look at this field or fix a set, which is a subset of f. And I'm going to pick one point from this set uniformly at random and query f on that point. And I don't know what else to do, so I'm going to pick a point uniformly at random. So in the univariate case, I know what is the probability that this is actually a 0. So I'm going to pick one point from the size set S. So at most d by S is a cardinality of S, right? Because it has at most d roots. So only in d of them it can be 0. Now this also appears to hold over multivariate polynomials. It's not a hard thing to test, but you have to use a proof by induction. So you have a polynomial on n variables with coefficients from the field. It has degree d. This polynomial is not identically 0. If it is identically 0, no matter where you query, you will get 0. And the problem is the polynomial is not identically 0 and you are trying to query at points which are roots. And S is some subset of f. And if I pick a set of so I want to pick a substitution to x1 to xn, right, which is a1 to an. If I pick a1 to an uniformly at random from this grid, which is the Cartesian product of S, then the probability that I will incorrectly query at a root is at most the degree by s. So this is not hard to prove. The base case is the univariate, which we have already done. You have to assume induction and then inductive hypothesis, and you can prove by induction. So what does this say? If I pick A1 to AN from a reasonably large enough set, so if coordinative S is like D plus 1, then there is definitely a point here such that f of A1 to AN is actually non-zero if f is not identically 0. But this requires me to pick a point A1 to AN from this large enough set. So this, each of them has cardinality at least D plus 1. So this whole set has cardinality like D plus 1 to the n. So this says that if I look at a grid of that large size, right, then definitely I will have one point at which it is non-zero. So in univariate case, it was easier because the number of variables was just 1. So there exists a set of size D plus 1 to the n that contains a witness to the non-zeroness of f. Right? Such a set is usually called a hitting set. So it's one set that definitely hits the polynomial. But this is quite large even when the degree is, say, 2. Right? This is like exponential in the number of variables. So you want to ask, so if you want to efficiently design an algorithm, you should say that given a polynomial, here is a small set such that if I search within this set, if the polynomial is non-zero, then I will find a witness to that non-zeroness of f in the small set. You cannot run over this large set computational. Right? So you want to ask, is there a small set, small hitting set? Small usually is polynomial. So what is the question? You are given n varied degree D polynomials. Since we are talking about polynomials, we can also assume that they all have small representations. Okay? So these are all computed by circuits of small size, say size s. Can we construct a hitting set whose size is polynomial in n, s, and d? Okay. So one other thing is, for example, I know that there is a set here that has large size, d plus 1 to the n, that works. Right? If you ask me what the set is, I can actually describe the set to you. 1, 2, so on up to d plus 1. Right? The Cartesian product of this set. So you also want that, see, you cannot say that there is a small, so we already know that there is a small size. So the answer to this question is partially yes. So it was proved by Haynes and Schnorr that if you give me an n varied degree D polynomial that is computable by circuits of sizes, there exists a hitting set of small size. Similar to the counting argument we did, but it should be a dimension counting because we are over infinite fields. But if you ask me what that set is, I cannot tell. Right? So you have to actually look for the set. So we want that set to be explicit in some sense. So if I ask you what is the point, you should be able to describe it via an algorithm. So that computationally we can make this work. So this statement here is a very popular lemma. It's called the polynomial identity lemma. If you are introduced to algorithms, then this gives a randomized algorithm to test whether a polynomial is identically 0 or not. Pick a point uniformly at random from this grid, substitute. With high probability, you will get a non-zero value if the original polynomial was not identically 0. So we don't know how to de-randomize this algorithm or get a deterministic algorithm. If you have seen algorithms, but if you are not introduced to algorithms, then this is the question. Right? Given n varied degree D polynomials computable by circuits of sizes, can you construct a hitting set of small size where I can describe the points efficiently? Okay, so probably that's all that I had to say.
The application of permanent, I mean, it is a nice polynomial with n square variable. Other than?
Okay, so it has some applications in computer science. So maybe I'll say, for example, if you want to count the number of perfect matchings in a graph, in a bipartite graph, or let's say a bipartite graph you have, and I'm not sure if you've heard of matchings in a bipartite graph. Have you heard of graphs? Yeah. Have you heard of bipartite graphs? Okay. So those are sets like this, right? So the vertices are u1 to un, and the vertices are v1 to vn. So you can ask about perfect matchings in graphs. So matching is a set of edges, right? It's a vertex disjoint. So you can think of these as, I don't know, students and these as colleges. Some students want have preference to some colleges. So depending on that, you want to match a student to this college. Right? So a set of edges, so this edge, that are vertex disjoint. So in some sense, you can match only one student to one college, or hospitals to beds. You can't put two people in the same bed. Right? So a set of edges that are vertex disjoint, they form a matching. Perfect matching is one where all the vertices are involved. So every vertex is matched. So every student is assigned a college. Right? So if you want to count the number of perfect matchings in a graph, right? So then you can say that there is a matrix whose permanent is actually this answer. So the matrix you should be able to obtain from this graph, something like depends on the adjacency matrix of the graph and so on. So in fact, Valiant showed that all counting problems can be described via permanent in a very abstract sense. So I'm not describing it formally, but all counting problems similar to this. If you want to count the number of satisfying assignments to a formula, right, then those things can be expressed as the permanent of a certain matrix. Of course, the matrix will depend on the problem. This is one example. So in fact, given a graph, you can also construct a matrix such that the graph has a perfect matching if and only if the determinant of that matrix is non-zero. It's called the Tutt matrix. It's described by William Tutt. Given a graph, I can construct a matrix that's based on the adjacency relationship such that that graph has a perfect matching if and only if the determinant of this matrix is a non-zero polynomial.